So about the history of the computers, which is the first question, from the first generation to the latest developments. So we're going to begin with the first generation of the computers, and looking at this one, the first, the main innovation was the introduction of the vacuum tubes, which were used for digital logic elements and memory, and also for power distribution. So in the first generation of computers, I think we would have to examine the most famous first generation computer, and that is the IAS computer structure. We are going to examine its structure, not exactly the computer. So the fundamental design approach was first implemented in the IAS computer, and looking at the IAS is the prototype of all subsequent general purpose computers. And looking at its structure, as you can see, looking at the structure of the IAS, we have the arithmetic logic unit. Below here, we have the control unit, program control unit. We have the main memory, the input-output devices, and you see there are data channels connecting them. So we also have the main memory. I guess I mentioned about it earlier on. So looking at the inner parts in the arithmetic logic unit, we have the SC, that is the accumulator register, the MQ, multiply quotient register, the MBR, that is the memory buffer register, the IBR, instruction buffer register, the PC, program counter, the IR, instruction register, and MAR, that is the memory allocation register. As you can see, there are control circuits and the control signals. So the main memory labeled M, the input output equipment, and so looking at its structure, we can mention a few of the uses of the I think the registers. Okay, before going to that, I think we can look at we can examine a few parts. So since there was this was the computer was mainly designed for mathematical operations, so it should have specialized organs for just the operations, and that is the central arithmetic unit. That is the arithmetic logic unit, and as you can see, it's the first part of the computer structure. So second, yeah, if the device is to be all purpose, then a distinction must be made between the specific instructions given for and then defining a particular problem, making sure instructions are executed, and that is the part labeled CC. So third, since this computer is going to be making very heavy calculations, and I think that was the main aim for the design of the computer, then it should have a very large memory to store data and help during the processing of the data. And that is where the main memory part comes in from, and that is the part labeled M. So of course, the device must have organs to transfer the data from its specific parts, like from C to M, then from M to the ALU, then from the control unit to, then from the input output equipment. So it must have a specific part for that, and that's where the instructions and data, the cables come in from. So lastly, that is the fifth one. It must have a specific data paths for transferring data from C and M into R, and from R into C and M. So, and that is the last part for, I think that is it should be labeled, I think, O, and I don't see it indicated. So but then we can indicate it at any other time. The main concept is to identify the parts. So as I told you that the memory of the IS consists of over 4096 storage locations, and called words, by the way. Yeah. And there is a definition has a word, but then I think a word is a memory location, so we shouldn't go into that. So the uses of the different registers, we have the memory buffer register, the MBR, and this contains a word. A word, remember, is a memory location to be stored in memory or sent to the input output unit. So then the memory address register, that is the MAR, this one specifies the address in memory of the word. So going to the instruction register, this one contains the 8-bit operation code instruction being executed. Then the instruction buffer register, this one is mainly employed to hold the right hand instruction from word in memory. Then the program counter, this one contains the next instruction for instruction pair to be fetched from memory. Then the accumulator register and then the multiply quotient. These ones I think are employed to temporarily hold operands and results of the ALU operations. So I think that is what we have for the IAS in. We also have the IAS memory formats, and I don't think we'd have to look at that. But the specific definition, like the standard definition, would have to give for a word. I think a word is an ordered set of bytes or bits that is the normal unit in which information may be stored, transmitted, or operated on within a given computer. Yeah, I think that's it for the first generation of computers. Then going into the second generation of computers, let me see. By then, I think we had to mention about the partial flowchart of the IS operation, and looking at it, let me see. So this is the partial flowchart of the IS computer, and looking at it, it has a total number of 21 instructions, and that indicates us having 21 arrows. And as you can see, is the next instruction is the IBR, yes, no memory access required. So it also has details, but I don't think it would be necessary to go into the details of the partial flowchart of the IS operation, because that would also require us going through the details of the IAS operation, and which we haven't done. So I think we'll go to the second generation of the computers, and that's it. Going to the second generation of the computers. Let me see. So going to the second generation, I think in the second generation, the main man, the greatest invention, the key thing is the introduction of the transistors. So that these transistors replaced the vacuum tubes in terms of the functions and then the uses. So, but then the transistors, they were smaller, they consumed less power, they were cheaper, they generated less heat. So, and the transistor is a solid state device. So, going to the characteristics of the the second generation computers, there was an introduction of more complex arithmetic and logic units, and then the control units also. So, and there was also a high use of the programming languages, which wasn't seen in the first generation of computers. So, and there was also a provision of system software with a computer. So, and then talking about the access time reduced from 30 microseconds to 1.4 microseconds. To the human eye, or to a human, that doesn't make so much of a difference, but then to a computer, that would be so much of an improvement. Talking about the multiplexer, this was a new feature that was introduced in the second generation of computers, and this wasn't evidenced anywhere in the first generation of computers. So the I think the representative of the second generation of the computers would be the IBM 7094, and looking at its configuration, it's quite a bit okay. It's a bit complex. But there it is. That is the IBM 7904 configuration, which I don't think it's necessary to examine it or to go into the details of the configurations. And that would take us to the third generation of the computers. In the third generation, which I haven't, of which I didn't summarize the notes, I think I'll just have to go plain about that or go brief. So in a third generation, the main man is still the main character. I think this was the introduction of the integrated circuits. So the integrated circuits, this was like the definition of the third generation, by the way. Yeah. The gates and memory cells, we also have to talk about them. I think there were the fundamental types of components that were required in the ICs. that is the integrated circuits. But then by connecting a large number of the fundamental devices, now we are talking about the gates and memory cells, we can construct a computer we can relate to our four basic functions. And remembering that the basic functions are data storage, data processing, and then data movement, and then the control of the data. So the data storage was provided by the memory cells, the data processing is provided by the gates, and then the data movement, these are the parts among the components that can be provided in so many ways, that buses, that data cables, Then the control, that is obvious, that explains itself. So you could be wondering what a gate is. So a gate is a device that implements a logical function or a simple boolean. Then the memory cell also, the memory cell is a device that can store a single bit of data. So the third generation of computers leads us to Moore's law, and Moore's law was it comes with a number of integrated circuits increasing over a certain period of years, and so it states that Moore's law states that the number of transistors in an integrated circuit doubles about every after no the number of transistors in an integrated circuit that was about every 2 years. So the Moore's law, we have a graph there is a graph that we can use to illustrate the law, this one, and we can say that the graph is of growth in transistor count on integrated circuits, and you can see this is on the vertical axis we have the transistor count, though not labeled. On the lower axis we have the years. Let me see. So on the lower axis we have the years, and we're starting from 1970 to 2010, but then the graph could be extrapolated to reach to the latest, and as of now that is 2023, but then the law still applies, and there's a graph, the extrapolated graph, but you can as well do it. You can extrapolate the graph, that would be up to you, but it still follow the law. And Moore's law has certain consequences. Moore's law has certain consequences. Yeah, Moore's law has certain consequences, and we are talking about the cost of the computer logic, memory circuitry, and this fall but at a very dramatic rate as the years went on. Then the reduction in the power consumption is also a major factor. I think it's one of the consequences. By the way, there was a very great reduction in the power consumption. Then the computers became smaller and more convenient to use in a variety of environments. What are we talking about here? There are so many computers. Phone is one of the computers that are becoming smaller and smaller each day that passes by, depending on the need of the final end user. And then there are smaller computers like the digital cameras and the CCTV cameras. Okay, it depends on what you want, but then there's very small computers to the size of insects, the smallest, one of the smallest insects. And okay, for example, an ant, something like that. But then that isn't our main point of concern. So the electrical path length was also shortened, and this increases the operation speed. So with more circuitry on each chip, there are there are fewer interchip. There were also fewer interchip connections, and this is also another consequence of Moore's law. Yeah, and I think those were the consequences of Moore's laws. We've also looked at the graph. So, and I think that leads us to the next generation. I think I should take back this floating window. Yeah, this leads us to the next generation of computers. I think that is. By the way, in the third generation of computers, we could examine the IBM 360 system, which has its own characteristics, and this was the international business machine. Was a great invention. We have to agree. Yeah, but then we won't go through it. So going to the fourth generation, of computers. This starts from I think. So, so the fourth generation of computers starts from 1974. Yeah, I think this starts from 1972 onwards. The main characteristic introduction was the intro. So looking at the Intel X86 architecture, that goes for the second question. So the current x86 offerings represent the results of decades of design efforts on complex instruction set computers. That is the CISCs. That is a short form we could use. This x86 incorporates the sophisticated design principles once found on only mainframe and then the supercomputers, and serves as an excellent example of the CIS design. So an alternative approach to the processor design is the RISC computer. So the ARM architecture is used in a wide variety of embedded systems and is one of the most powerful design RISC-based systems on the market. Almost 40 years after its introduction in 1978, the architecture of the x86 continues to dominate the processor market outside of the embedded systems. So you could remember that ARM is for mostly the embedded systems, unlike the x86 architecture. So would like to have a look at the highlights of the evolution of the Intel product line. So beginning with the 88E, so this is the world's first general multi-purpose processor. Definitely it was an 8-bit machine. Going to the 8086, this was far more powerful and it was a 16-bit machine. And in addition to a wider data path and larger registers, it spotted an instruction cache or a queue, and that prefetches a few instructions before they are executed. So going to the 8286, this is an extension of the 8086 machine design, enabling addressing a 16 MB memory inside of just 1 MB. So going to the 8386, this is Intel's first 32-bit machine and a major overhaul of the product. So with a 32-bit machine architecture, the 8386 rivaled the complexity and power of mini computers and mainframes introduced just a few years earlier. So going to the 804486, this introduced the use of more powerful and sophisticated cache technology, and and this one also favored the pipelining more than the earlier Intel product lines. So then going to the Pentium, Intel introduced this as for superscale techniques, which allowed multiple instructions to be executed in parallel. Then the Pentium Pro continued to move into superscale organizations, and this was begun by Pentium. And this one used the aggressive use. This one employed the aggressive use of registers. Uh, Okay, brand prediction and data flow analysis and speculative execution. So then going to the Pentium 2, this one incorporated an Intel MMX technology, which is designed specifically to process the videos, audios, and graphics, such stuff that fall into that category. Then the Pentium 3, this one incorporates additional floating point instructions. Then the streaming SMID extensions, instruction set extension added 70 new instruction designs to increase performance when exactly the same operations are to be performed but on multiple data objects. Typical applications are digital signal processing and then graphics processing. Going to the Pentium 4, this one includes still additional floating points. So, uh, what else? Maybe the core and the core one, and then the core two. So for the core one, it was the first Intel x86 microprocessor with a with a dual core, referring to the implementation of two cores on a single chip. So then the core 2, this one extended the core architecture to 64 bits. So the core 2 quad provides 4 cores on a single chip. More recent core offerings have up to 10 core chips. An important addition to the architecture was the advanced vector extensions, instructions that so provided a set of 256-bit and then the 512-bit instructions for efficiency of the processing of vector data. So going to the ARM architecture, so the history of this one isn't so okay. The history of the evolution of the ARM architecture, it's more of about the inventors than what the machine is about. But at the moment, the ARM architecture is the most widely used architecture. It is embedded in smartphones designed by both the Android and then the iOS. So the ARM is a family of RISC-based microprocessors and microcontrollers, and these are designed by the ARM Holdings, that is in Cambridge, England. So the company does not make processors, but instead designs microprocessors and multi-core architectures and licenses them to manufacturers. So specifically, ARM Holdings has two types of license for products, and that is the processors and then the processor architectures. So for a processor architecture, the customer buys the rights to design their own processor compliant with the ARM's architecture. So ARM chips are high-speed processors and they are known for their small size and low power requirements. And that is one of the advantages they possess. They are widely used in smartphones and then the handheld devices. The ARM chips are the processors still, as I told you, in the Apple popular iPods, the iPhone devices, and I and are used in virtually all Android smartphones as well. ARM is probably the most widely used embedded processor architecture, and indeed the most widely used processor architecture of any kind in the world. So for the Intel X86, you realize that it was for the non-embedded process architectures. But then the ARM is for the embedded, and that's where the difference comes in when it comes to the domination of the world market. They have both dominated, but then in different categories. So the origins of the ARM technology can be traced back to the British-based company, and that is the Acorn Computers Company. The success of this contract enabled the Acorn to go on and develop the first commercial risk processor, that is the Acorn RISC machine, and that is the ARM we are talking about. The first version, the ARM1, became operational in 1985 back then and was used for internal research and development as well as being used as a coprocessor in the BBC machine. So, uh, the ARM design matched a growing. We've not talked about the early stage. In the early stage, the Acorn used the computer VLSI technology to do the actual fabrication of these processor chips. But the VLSI was licensed to market the chip on its own and had some success in getting other companies to use the ARM in their products. But and remember, they offered the what the ARM. They offered the ARM in their products, but then at a lower cost. Okay, particularly, but it's an embedded processor. So the ARM design matched a growing commercial need for higher performance, lower power consumption, small size, and low cost processors for embedded applications. And I think these are the advantages of the ARM. So, but further development was beyond the scope of Acorn's capabilities. Accordingly, a new company was organized with Acorn, the VLSI, and Apple Computers as founding partners, known as the ARM Limited. The Acorn RISC machine became the advanced RISC machine. Yeah, and that is it for the ARM. And I guess that's where we stop for our presentation about the architectures of the Intel X86 and then the ARM computer.